zeta of...
No,
No?
will be, will be. The blackboard is not too wide, so zeta of 4 doesn't have space there. Okay, so thank you very much for the invitation. So I want to say just what I'm going to talk about. So there is some connection. So on one hand side, you have this cluster varieties. Actually, I kind of wrote it on as a title. So there is a cluster varieties and there are polylogarithms. And we know very well that there is connection between these guys and dialog here. And from my perspective, the structure of cluster varieties is basically built on this connection when you consider quantum dialog. But it turns out that all polylogs appear in this subject, and this relation is useful at least for understanding polylogs, and that's what I'm trying to explain. But before I go to that, I want to explain, I want to start from a little bit different perspective. So we have symplectic variety. So we have symplectic variety, x omega. So omega is symplectic form, or just two form here. And in some situations, and cluster varieties is a particular example of the situation, we can do better than symplectic form. So it turns out that symplectic form has some motivic origin. And so I want to give, first of all, an example. I want to explain in what sense it has motivic origin. And then the whole subject of the talk is to explain, this was known, that if you consider e to omega, it also has motivic origin. And this is a much more stronger and subtle statement than the one I'm going to explain right now. Okay, so it's a kind of, I'm just saying that on arbitrary varieties you can do nothing else. If you want to consider symplectic geometry, just consider the two form. But in some situations you can do better, and you can do much better. Okay, in order to explain what kind of structures we talk about, let me start with the definition of Milner K-theory. So we take F to be any field. And then according to Milner, so we define the ring, Milner ring, K dot Milner of F, to be just tensor algebra of the multiplicative group F star. This is a multiplicative group, understood as a abelian group, divided by the two-sided ideal generated by so-called Steinberg relation. So for example, if you talk about the group K2, so the group K1 is just F star, it's not nothing fancy. But sorry, I forgot to say one more thing. So this turns out to be the same as exterior algebra of this multiplicative group divided by the ideal generated by the same relation. So this relation implies skew symmetry condition. And so if you want to consider the group K2 of F, so this is just, you can say F star wedge F star, wedge over integers divided by subgroup generated by these strange elements. Now the point is that if you have Milner K-theory, there is a map to differential forms, d log, differential log, which is a map from Kn of F to omega n, and forms, this is how you denote it, F over Q, color differentials. So for example, if F is a field of functions on a variety, you just get differential n forms on this variety. And it goes in a very straightforward way. So A1, which is on wedge AN, goes to dA1 divided. A characteristic can be 2. It doesn't have to be 0 characteristic. It goes this way. And of course, the point is that the Steinberg relation goes to 0, which is entirely obvious, because if you have 1 minus x wedge x, it goes to d log of 1 minus x wedge d log of x, which is of course 0. It's just you have dx and dx twice. Okay, and so the point is that in some situations we can upgrade to form to element in K2, and actually we can do better than that. So I'm going to give, first of all, to give an example of a variety where we can upgrade symplectic form to its kind of Motivic version. So this variety called conf n v2, and this is just collections of vectors L1 and so on Ln, which live in two-dimensional space. This is two-dimensional space over some field F, and in generic position. Generic position means that any two is linearly independent, and considered modulo the action of the group SL2. Now, who is SL2? So we also pick here symplectic form in this two-dimensional vector space. So this is SL2 with respect to this symplectic form. Okay, so that's the space, and I claim that this space has two forms. It's not quite symplectic structure. Depending on n, it can have one-dimensional kernel. So the quotient by the null relation will be symplectic. It doesn't matter. So I want to explain how to construct, first of all, symplectic, these two forms there, and secondly, how to upgrade it to its Motivic version, and then what's the statement I'm going to try to understand. So let's do the first example. Let's consider the case when n equals to 3. In this case, we have, I just picture these triples of vectors by this picture. And so I can just write down the corresponding formula. It's just differential of omega of L1, L2, wedge differential of omega of L2, L3, plus differential of omega, the word omega, okay, L2, L3, plus cyclic shifts, L3, L1, plus differential omega of L3, L1, wedge differential omega of L1, L2. So it's clearly a two-form. And now if I want to make this two-form Motivic, nothing can be better, and nothing can be simpler. Just do this. And now it becomes Motivic. Because now it sits in wedge 2, as you clearly see here. And no more statements. So we just leave it to wedge 2 of F star. That's quite trivial. But now let's do the situation when n equals 4.
Where does it live now?
It lives, so you have a space. And you live in the wedge 2 of the functions on this space. Because for every triple of vectors, this is a function on your space, right? And so we just consider this function is non-zero by assumption. We have generic vectors. And so we just live in the wedge 2 of functions on this conf 3v2 star. Okay? Now let's consider the case n equals 4. Then
Are you adding these? Is that the sum?
yes, I'm adding that because as I told you, my basic object is F star, tensor F star. This is an abelian group. And so I'm using addition in the wedge square of F star. Now, how about n equals 4? Then we draw this picture. So L1. Well, I mean, officially I said, I explained to you what is K2 of the function field. So if I want to stick to that, I say this. But in this case, I just get element of wedge 2 of the ring of functions, multiplicative group of functions on this variety. Okay. So it's a little better than what I'm saying. Okay, so now let's suppose that we have 4 vectors. And then there are actually 2 ways to proceed. So we can draw one picture like that, and we can draw another picture like that. The same L1, L2, and 3, and L4. And we can triangulate it this way, or we can triangulate it that way. And as soon as we did this, there is a natural way to proceed. We can take the 2 form here plus 2 form here, or we can take 2 form here plus 2 form here. So let's denote this triangle like T1, this is T3, this is maybe this is T3 and T1, this is T2, and this is T4. And so if this is element W related to my triangle, then I can just write suggestions that I say that W1 is just this W first triangle plus W of the second triangle, which is just T3. Or I can write here W of T2 plus W of T4. So both elements, they lie in the wedge square of the ring of functions, but they're different, unfortunately. So, but nevertheless, if you consider the corresponding, so let me call this maybe W, and this is W prime. However, if you consider d log of W, this is the same. Turns out this needs to be proved as an exercise. This is the same thing as d log of W prime. And so what happens that this explicit formula, like either this or that, defines your symplectic structure. I would rather say two-form, pre-symplectic structure. But if you try to lift it up to the wedge square, then they're actually different. But if you project it to K2, so I claim, which I'm going to prove in a second, that the classes of W and W prime in K2 coincide. So I'll prove this in a second, but that's the point. So now I can associate this class. It's either W or W prime, and so it lives in K2 of the space which I consider. Which again you can put here a function field, but then it's regular on the whole space. It doesn't have any material ratios. So that's kind of first approximation to the idea that you have to make it Motivic. So it already lives in K2, which is a more subtle object than just two forms. All right.
So what does it mean, log of W, d log of W?
Didn't I define this? It's defined here. So there is a map d log which goes from the algebraic K-theory to differential forms. And it has a property that it takes these two different elements and produces the same differential two form.
When you use the word Motivic, you mean that it comes from K?
That's a little later. I use the word Motivic for purpose, but so far we didn't describe what Motivic is. Okay, but also, so this statement needs to be proved, and so let me kind of tell you what the proof is. So what we need to prove, we need to prove that the difference between those two guys is a linear combination of Steinberg relations. And it turns out that just one Steinberg relation. And so I just emphasize that this is the strongest statement. If you look at the differential form, of course it proves that the differential form to form will be the same. But it's a much stronger statement that it's the same. It's a statement that its class in K2 is the same. So let's see what's the reason for that. The reason is important, as important as the statement. And so the reason is the following. So we consider, let's take X to be the cross ratio of these four vectors. This is cross ratio. And so I claim that if you consider this particular X, then 1 minus X wedge X equals this W minus W prime. And so that's a proof. And again, so you can try to check why this is so. This statement is equivalent to the Plücker relation between this is Plücker coordinates and the Grassmannian. And so the statement is just equivalent to that. Let me just write one sentence why. Because how you define the cross ratio. For example, you can do it this way. Let me put here 3. Here 2 and so if you take this wedge, the same thing, I'm not going to write it down. So you can use Plücker relation in order to replace this again by a fraction, because the numerator minus denominator will be again a product of two omegas by Plücker relation. And then you can just open the brackets and you will see that you get exactly the difference between two forms. Okay. Now, this is a simple example, but it immediately provides you claims that the same is true on the whole space of configurations. That if you now consider conf n of V2, then it also has a K2 class. And this follows from what I said, because how you construct this class, let's suppose you have 5 vectors. Then you take any triangulation you like of the space. And then if you take any other triangulation, then they're related by a flip. And we already we define our form omega. So let's have the triangles T1, T2, and T3. Let's just divide W related to this. It's just WT1 plus WT2 plus WT3. And the claim is that as element in K2, it's independent of the choice of the triangulation we put. And the reason for that is that it was already proved for n equals 4. So it follows from that. Okay? Now you can do even better than that. So you can try to keep. So again, the idea is that you have a 2 form. Then you replace this 2 form by, so to speak, some kind of final object, lambda 2 of f star. Then you prove that in K2 it's the same, but now you want to keep the reason why it's the same, you want to put it as a part of the game. So let's do that. So in order to do this, we introduce notion of a Bloch complex. Bloch complex. It's complex which was essentially introduced by Spencer Bloch. And so it's defined as follows. So it looks like that. So we want to define a subgroup which is called B2, the Bloch group. And we want to map it to the group which is wedge 2 of f star. And how we define this group, we say that B2 of f is quotient of free abelian group generated by f star, let's say -1, by a certain subgroup. And the map, delta, you want to define as a map which takes the generator and goes to 1 minus x wedge x. And so you see what we're doing. So I didn't tell you yet what this R2 means, but no matter what, the co-kernel of this map delta is, by Milner's definition, K2 of f. And so what we're trying to do, we're trying to construct resolution of K2. So we're taking here all the Steinberg elements. We parameterize they parameterized by elements of your field f, and we map them there. Now I still need to explain what is R2 of f, and this is informally the subgroup of all linear combination of Steinberg elements which die under this map for free. The formal definition is this. So you take 5 points on projective line, and then you consider alternating sum of the cross ratios of 4 of them when I is omitted, and you declare that such elements span, by definition, this subgroup R2 of f. So now we have complete definition, except that we have to prove that these linear combinations die under this map, which is not exactly obvious. So, however, the proof follows from what we did before, because let's just write down the pictures for all these pentagons. So we have 5 pentagons. And so we do flip here, then we do flip like that, then we do flip like that, then we do flip like that, and then we come back. So we have sequence of 5 flips of our triangulation, and then we come back. But now notice that when we do flip, so let me number again this elements as like L1, L2, L3, L4, and L5. And let me note This blackboard is a little small. So if I have just some foregone in my picture with diagonal E, then I can associate to this cross ratio, which I will call x sub E, which is cross ratio of this vectors, this, and this, and this. Okay? And so now I have this element of H2 here, element of V2 here, and the difference between them, from what I said, it's x related to this diagonal. So let's call it x14. Now, if you do it here, it will be delta related to the other diagonal we flipped. So x13 and so on. So you'll have 5 delta x's here. But their sum is obviously 0 because when you do this, delta of this is difference between this class in lambda 2 and this class lambda 2. When you sum them up, you get 0. But on the other hand, this means that sum of those deltas equal to 0 in lambda 2 of f2. And this proves that actually delta takes 5-term relation to 0. Okay? Is that clear? Okay. Okay, so far so good. So now I can say what do I mean by at least way 2 Motivic complexes. And so by this, so this Bloch complex is one of the best way to think about this. And the main point is a theorem behind this, which is due to Suslin, which says, let me say that this group lives in degree 1 and this group lives in degree 2. So as we already seen, H2 is K2, but if you take H1 of this complex, let me just denote it this way, then this is so-called K3 in the it will be a little light. So let's take just modular torsion. Then it will be K3 in decomposable modular torsion. What is K3 in decomposable? This is by definition quotient of K3 Milner, quotient of Quillen K3 of F by the Milner K3, which naturally embeds there. And so we get the group K3 as the kernel of this map. And as I said before, H2 of the same complex by definition is K2. So now we see that we understood after this not only K1 but also K2, K3 indecomposable, and the rest of K3 just K3 Milner, so we get up to K3. Okay, Viti, you have? Huh? K2 Milner is no different than K2. They're the same by theorem of Matsumoto. All right, so now I can explain what I want to do. So in the situation which we considered, let me draw this picture again, that you have, let's suppose that we have a polygon. So I can assign to polygon a presymplectic form, 2 form. But now I'm trying to say that I can leave this to form to this Motivic avatar. So I can, and what it means is precisely the following, that I can, I'm saying that this to form is written in a different way in different coordinate systems. Coordinate systems are parameterized by the triangulations. It lifted for each triangulation to this term of this complex. And whenever 2 triangulations are related by a flip, it's canonically lifted to element of this group in this complex. And then if you think about all triangulations of a polygon, they have some geometric shape. This is called Stasheff polytope. So I remind you, what? That there is notion of a Stasheff polytope, let's call it Kn, n-dimensional Stasheff polytope. And you can say that it's a convex polytope, but combinatorially, its vertices is by definition the same as triangulations.
Yeah, not to be confused with K-theory.
Yes, and with also with this K equivalence, I forgot who was talking. So there are many cases. So this is, but it's traditional. So it's triangulation of some polytope. In this case, it's polytope with n+3 vertices. But now, if you want to consider edges of this polytope, then it's going to be flips. So you can say that the edges flips of triangulations. But now you want to do better, and you say that p-dimensional faces are the same as partial triangulations with exactly p edges missing. Okay? So, for example, edges are flips. Now, the key fact about Stasheff polytope is that it's a convex polytope and therefore it's contractible. And so now we can try to play in the following game. We can say that let's just consider this Stasheff polytope. And the vertices of the Stasheff polytope, we assign to it this element in lambda 2 of f star. We assign to one-dimensional faces elements of the second group in the complex. But when we go to two-dimensional faces, what are two-dimensional faces? There are two-dimensional faces. They're geometric, they're again pentagons. These pentagons are everywhere here, and squares. So this two-dimensional face corresponds to the picture which I had here, 5 flips of the triangulation, and this corresponds to flips which you do far away from each other. And so if you want to play this game, of course, you have to assign to these faces a 0 because your complex doesn't go anywhere. And that's exactly how the Bloch complex is defined. It precisely defines such a way that this guy corresponds to 0 because it produces this relation, and this produces 0 for free. And so after that, I produced, this is what I mean by saying that this symplectic form has Motivic avatar. This structure, it is this Motivic avatar. So I want to remark that, we'll talk about this later when I will talk about cluster varieties, that exactly the same thing happens for arbitrary cluster variety. But now I want to say, still talking about this example, that I want to consider the not only the symplectic form, but it's exponential. So let's take.
Do you want to say who is the cluster variety here?
The cluster variety here is conf. This is my cluster variety. What? Configuration space of n vectors in two-dimensional space. Now, the point is to say that now I want to consider E of this W. This W is, let's say, for now it's symplectic form. So if you want to consider E to symplectic form,
It's omega, no.
huh?
It's omega, not double.
Well, let's say omega. If you're saying so, okay. That's not a problem, but you want to upgrade this to E to W. That's all. So I win, you see. But this E to W wouldn't make sense because remember how the game works. So you take each triangulation. For each triangulation, you produce W related to this triangulation. It's going to depend on the triangulation. And so what you wanted to do, you wanted to consider this big Stasheff polytope. So let me draw a picture for the three-dimensional one. It looks like that. This is.
I'm sorry to interrupt, but can you repeat your point about these higher coordination faces of the Stasheff polytope? I understood the role of the.
Yes. What was the point?
You somehow emphasized something about faces of arbitrary dimension in Stasheff polytope that you can assign to them something or.
Zero.
Okay.
Yes. So to zero-dimensional faces, this lambda 2 of f star, which you see from symplectic form, for one-dimensional faces, the reason this symplectic form is invariant, and for two-dimensional spaces, you assign 0, and this is a very non-trivial effect because it's equivalent to the definition of the Bloch group.
Okay.
So what you assign to them, really, you assign element here.
And then we stop it.
I don't stop. I'm just saying that, as Dima said, so I assign to all high-dimensional faces zeros. That's okay. All right, so this is a three-dimensional Stasheff polytope. And so if you want to do, why I choose three-dimensional? Because if I take two-dimensional, the game stops there. But here we have three faces, and I can consider, for example, W square. So this is a four form. I mean, Vita would say that I originally consider omega square. So it's a four form. But I consider subgrade to H4 of f star. And so I start to playing again the cohomological game. I write here H4 of f star. Now I need to, if I consider, so that's what I put here, but if I consider any h, then I need to put the reason why these two elements in H4 of F star give you 0 in Milner K-theory. And this reason universally is given by this group, because there is a map which on the generator takes x sub 2 tensor y1 wedge y2 to 1 minus x wedge y1 wedge y2, all right? And so the co-kernel of this map is Milner's K4. And so if I want to prove, and this is indeed the statement is that this e to omega makes sense as Milner K-theory, that it does not depend on the choice triangulation. It's a first statement. It's not the main statement. But if I want to do this on the level of complexes, so I have to tell you how to put some elements from here on one-dimensional faces. Huh?
What is e to omega?
What?
What is e to omega?
E to omega, first of all, the first question is what is omega? Because there could be questions about this. Omega t, I'm answering. So omega t belongs to lambda 2 of your function field, okay? Oh, sorry, I always, that was your point, right? I mixed up omega and w. I'm talking about, this is w, this letter w. So wt is element of lambda 2 of f star. And now I believe, Andrei, you just, you understand, right? So e to omega is element of wedge algebra of f star.
No, but it's like the coefficients of this exponential are really important?
They are important, so we have to take the wedge algebra of f star and tensor.
The question is there 1 over n factorial.
Yes.
So you
Yes, there is 1 over, so you wanted me to put here 2 factorial, okay. They're important and not important. I mean, for the statement, they're not important. They're important in general, but I can just skip them when I'm talking about this Motivic avatar.
How do you divide? You don't divide.
I don't divide by tensor with q.
This guy's in square.
The main point is to understand this guy. Then to divide is very simple. Just declare that you can do tensor with q. All right. So this guy, omega 2n, lives in wedge 2n of f star. And now I want to say, so now I want to start this delooping. So I want, Andrei, what's your question?
Where are you going to use that this is exponential, not some other series?
No, nowhere. All right. On today's lecture, it will not be used anyway because I'm not going to write you today explicit formula. But in general, you can just say that I'm going to study this some q, the q's powers of my 2 form. Okay? And so, but even second power. Okay? Now, how we study second power? So we take second power, it lives here. In order to prove that it's the statement that it defines, listen guys, so wait, maybe you ask me question or, because otherwise I think that that you don't understand. Okay, so if you want to prove that this is element in K4, you're supposed to provide the reason why it's this is so under the flip. So you're supposed to find something here which lives on every edge. But after you did so, you're not done, because then you still have faces. For example, you have 2-dimensional faces, and you're going to provide reasons between those reasons, which tells you that you're going to construct map from the chain complex of the Stasheff polytope to some kind of complex here. And the main issue so far that I didn't tell you what the complex is. So this complex is the Motivic complex. That's going to be the definition of the Motivic complex. And again, informally, it's a resolution of Milner K group. So you take this guy and put here the reasons why it's a Milner K series. Then you put here the kernel, so to speak, of this map. You write explicitly, and so on, so on, so on. And so now the general statement is that whenever I put w to some power 10, I can write some so first of all, I need to explain what kind of complex I'm talking about. But then I can upgrade the symplectic form to the guy which lives in the whole complex. And so this is the Motivic avatar of the power symplectic form I'm talking about. And and then the point is that this can be done not only on Stasheff polytope, but on any cluster variety. Now, why this is, what could be the use of this? So I wanted to present one theorem which is proved using this. So again, I'm not sure you're interested in this theory or not, because this is not talk This is not a talk on representation theory, neither with groups or without groups. And so the theorem is not about representation theory. Huh? Well, but I still wanted to explain how this machinery, how this idea works in application, because you will see at least some motivation to look at this Motivic complex and to these upgrades. Okay. So let me state the theorem, and then in the process of explaining actually the statement, you will see, you will start to see the definition of these Motivic complexes. So the theory comes from some, this is part 2, so to speak. So let me remind that the classical formula which says is that if F is a number field, then if you consider the zeta function, the Dedekind zeta function of this field F, and take its residue when S equals to 1, there is a classical formula due to Dirichlet which says that up to certain powers of 2 and pi, it's a product of a bunch of numbers. Most of them are rational. One of them is square root of rational. And the most interesting for us is this one. It's transcendental. So this is the class number of this field. This is the number of roots of unity of this field. This is discriminant of this field. And this guy defined as follows. So you take the ring of integers in this field, and then there is a map from here to the vector space R1 plus R2 minus 1. So nobody asked me a question, what is R1, what is R2, this means what?
Number of complex and
Huh?
embedded.
Yeah, good. So we define this map is defined very easily. So X goes just like Andrei said, so we have to take some embedding of your field. You have to apply this to a unit. You have to take absolute value in this embedding. You have to take the logarithm. And you have to do this when I is 1, so on to R1 plus R2. R1 plus R2. But then the sum of these numbers will be 0, and so this sits here as a diagonal. So we have a map like that, and it's well known that the rank, it's well known the following, that if you take OF star and divide it by roots of unity sitting there, then it's a free abelian group of the same rank as the dimension. And then you take this lattice, the image, this map is called the regulator. You take the image of this free abelian group because units die, and then you take its volume. The volume exists because it's just a coordinate space. It has canonical Lebesgue measure, and this is the definition of the regulator. All right. Now, if I want to explain how this works for other numbers, so I want to consider zeta f of 2, zeta f of 3, and so on. So two things must happen. So first of all, I have to explain what this is, and I have to explain what this is. And the second is easier task because there are polylog functions. So they're called classical polylogs. So Li n of z is just sum of z to k divided by k to n when k goes from 1 to infinity. And they can be written as integral. Oh no. And the important point is that what we are looking for, we are looking for a definition of replacement from this group OF star. Now, we kind of know where we should look for the definition because there is a theorem of Borel. It's 74 and another paper in 76, which follows an original suggestion by Lichtenbaum, which says that there exists a high regulator map Rn from the group k to n minus 1 of your number field to the group which is either R to R1 plus R2 or R to R2. And this is the case when n is even, and this is when n is odd. And then it says that the rank of this group is precisely the dimension of one of these vector spaces. And then Borel's theorem says that zeta f of n up to q star and some, up to q star, remember there are many numbers here, and also up to some power of pi, which is n times this number, let's call it dn. This is dn, it's either this number or this number. So then up to that, this is the volume of the image of this regulator map. So this answers the question where we should look for the replacement of OF star. This is the group Kn. And this doesn't say anything about how this map looks like. It says basically absolutely nothing about this. Now, the point is, this was the point of Zagier's conjecture, that there should be a similar result where the role of the log is played by polylog. And he had some formulation, which I'm not going to repeat. So I'm going to give you a little bit different formulation, which is a little bit more appropriate for what I want to say. And so in order to do this,
when we say volume of image, it is a co-volume.
it depends.
Well, I mean, it's a large
Volume of the quotient.
Yeah. But then, no, the real question is, so you have, like, for n equals 1, for example, you have k1 of f, which is f star. Yes.
Yes.
And there you had O f star. So
Excellent.
So
These cases are different.
okay.
Yes. You might have another remark. In this case, I have not these numbers, but I have this one. R1 plus 2 minus 1. It's also different. This is because zeta function has poles there.
Okay.
So some things go a little differently, but after that they go uniformly. All right. So so first of all, I wanted to explain what the goal is. So this function has a single valued analog. It has many single valued analogs. So let me write it so that David can see. So this is ln of z. This is either real part or imaginary part, exactly like n odd, when it's n is odd. It's real when n is even. It's imaginary. Of certain expression. So this is Li n minus k to z multiplied by k's power of absolute value of z. So here stands some rational number. And I don't really want to tell you what this rational number is, especially because there are several possibilities, finitely many possibilities, how you can put them for all of them. This is going to be a nice single valued function. And so we take any of them. Now, then what we want to do, we want to look for all functional equations of this function ln. And the bad news is that nobody knows how to write them when n is, I don't know what the world record is, but for n is 15, I'm sure nobody knows how to write any of them, except the trivial, that if you take ln of z plus or minus, plus minus 1 to n ln of z inverse, this is known to be 0. Other than that, nobody knows how to produce any single functional equation. On the other hand, when n is small, functional equations exist and we know all of them. For example, when n equals to 2, the functional equations... Explain a second. So when n equals to 2, the statement is this. That if you take this function L2, it's called the Bloch-Wigner function, then defines a map from B2 of C to real numbers. This is not a cheap statement. This means that L2 satisfies this Abel's 5-term relation. Because the way this group was defined, it was, how this map goes, I didn't tell you. So this is, remember, this is Z of C divided by this group R2 of C. And when it takes the generator here, Z, it goes to the value of the dialogarithm of Z. That's how this map is defined. Now, the claims that it factorizes through the descents to a map of the quotient means that this group is killed by L2. Yes, C star. So this is not very important. Because the function L2 vanishes on the whole real line, even. So that's the first statement. And the second statement, that's the answer to Andrei's question, that whenever you have any functional equation, and functional equation means that you have some identity that the sum of dilogarithm is 0, and it depends on parameter. I actually need to be a little more precise, but let me just state like that. If you have any functional equation, then it's a consequence of this one. So you can deduce any functional equation from the Abel's equation. It's a theorem. Okay? What?
It's easy to believe. Functional equation is a relation of some modular or some operators, right? So what
No, functional equation. So you have a function, L2. And you want to know relations which functions satisfy. So for example, I can write you a relation. L2 of z plus L2 of 1 minus z equals to 0. Okay? So you want to...
But you allow like z coefficients, you allow arbitrary coefficients.
As I said, so the arguments here are supposed to be rational functions with supposed to be functions with rational coefficients on some parameter t. Okay, so the functional equation by definition means. How can I write it?
The function equation for L2,
Yes.
equation will have two parameters, right?
That's okay.
So you can have any number.
You can have any number of parameters. Some L2, maybe with some rational coefficients here, of some functions fi, which depends, as Pasha said, on any number of parameters you want, but more than 0. So, so this sum equals to 0. That's a functional equation. Fi are functions with rational coefficients. All right?
And the coefficients are rational numbers.
Yes. Rational functions with rational coefficients.
No, in front of the
Oh yes, also rational numbers. Because otherwise, the statement makes no sense whatsoever, as you probably want to say, because you can take any two dilogarithms and add them with complex coefficients, get 0. But you consider only linear combinations with rational coefficients evaluated at rational functions which belongs to field Q of T1 so on Tn. Then the statement is that any identity like that follows formally from Abel's identity.
I also have a question. So you have log k of absolute value? I didn't understand. So
Yes.
You said you want to find a k such that this function
Is single valued.
But log k of absolute value of z is already real. Somehow you
Yes, but this function is multivalued. It's a product of Li n minus k and log k to z. So, and the summation starts from k equal to 0. That's the whole point. So you take Li n of z, and then you add some tail to it of known shape. And the point is that you can add such a tail that this will be a single valued function. And there are finally many possibilities about n over 2 how to do that in a way which suits me here. Okay? All right. So that's the situation. So we want to find all functional equations for the polylogs, but as I said, for n equals 2 we know all of them, but for n equals 15 we know none of them, and I believe we will never see any of them written on a paper. So they are very, very complicated, I think. But we know that they exist. So, but yet on the other hand, so you have seen that this definition of the second Motivic complex, it was about the functional equations for the dialogue, because it's basically used it. And so we want to get a way out of this as follows. So let's take F to be any field. And so let's, by induction, define the higher Bloch groups, Bn of F, to be the quotient of the free abelian group generated by F, or F star if you want, modulo some subgroup Rn of F. And this subgroup is supposed to be the subgroup of all functional equations, the same way as I said before. Now it has a definition. So we define it as follows. So we consider map, let's say from Z, let's do it with Q coefficients, Q of F to Bn minus 1 of F tensor F star. So let's call this map delta. And it takes generator X sub X to the same generator projected to the quotient tensor X. This is when n is bigger than 2. And when n equals to 2, you have to do 1 minus x wedge x. And you have to put wedge, you can put always here wedge product, but when n is bigger than to wedge and tensor, doesn't matter. So that's the map. And what we want to do, we want to take kernel of the map, but we don't want to take all the kernel because then we will kill actually the goal of this game. So we want to take only the part of the kernel which like that, which parametric, depends on parameters. And so in order to do this, the way you do this formally is this. So you take any combination with rational coefficients of some rational functions on one variable, which belongs to the kernel of this map. Let me call it delta n. But in the case when my field is a function field, so this fi, they belong to f of t. So I extend my field f to field of rational functions, and I consider any linear combination of such guys which die under this map. This is well defined because by induction this group is already defined. And then we just specialize element in the kernel in two different points, and we get the definition of this group Rn.
Delta n minus 1 probably. But like delta n minus 1 constant, right?
Huh?
You impose something here that phi is not a constant, or?
Just a second, I didn't finish the definition. So what we do, we take linear combinations of ni, and we take fi at some point t0 minus fi at some point t1. It's two different points. And so all combinations like that, by definition, generate Rn of f. Okay?
N plus 1 probably.
No. This is n minus 1. Okay, so why is this definition is sensible? I'm not going to go to all details, but basically if you write down the differential for this function ln, then you'll see it works like that. It will be ln minus 1 of the differential of argument of z plus something else, but this something else also kind of controllable. But if you look at this term, you see that by induction, if you take element which lies in the kernel, this will be gone, this will be 0. And so the differential of this function on any combination like that is constant. But then when you take its values in two different points, it must be 0. That's why we get functional equations. And so that's the definition of this group. Now, this definition allows me, so can I erase this if nobody objects? Now I can define the complex. This is polylogarithmic Motivic complex. That's a definition. And so it looks as follows. So you write this group Bn of f, map it to Bn minus 1 of f, tensor f star. Then you map it to Bn minus 2 of f, tensor wedge 2 of f star. And then you keep going. In the last moment, you're going to B2 tensor wedge n minus 2 of f star. And then you go to lambda n of f star. So I hope it's clear how this complex works, because, for example, here we take x sub n, and we map it to x sub n minus 1 tensor x. And again, you do the same thing here. Like this goes to this tensor this, and then you f star just identically goes. Yes, we skip b1. Yes. And the differential here is not x goes to x tensor x, it's x goes to 1 minus x, wedge the tail which you see here. So it always, in the end, it's a little different. Okay, so we have the complex, so it's well defined. Now the conjecture, let me write this conjecture here. The conjecture is how the cohomology of this complex looks like. And the statement is that they give you all algebraic theory in the way predicted by Bellinson. I mean, he somehow, one of his main contributions to theory of motives, that he understood how to match this potato motivic cohomology with pieces of the gauge theory. And so it should look as follows. So draw this diagram. So here you put the group F star, which is K1. Here you put the group K2. Here you put the group, this is GR wedge 2 of case 3. And so here you must put 3 groups. Here you must put 4 groups. Oh, so what you do, so the conjecture says that if you take I-dimensional cohomology of this complex B of Fn, then it's supposed to be GR with respect to certain filtration called the Adams filtration of K2 minus I of F tensor Q. And so that's the conjecture, and Beilinson conjectures that there exist such complexes which have exactly this shape. This is now known to some extent. We know that there exist such complexes, but we don't know that they terminate if you go to the left. So so far we think that they might have cohomology on the left. If they do, it's a big problem. But the complexes I'm writing down, they don't have this problem, and so they, by definition, terminates where they're supposed to terminate, and conjecturally are Motivic complexes, so give exactly the Motivic cohomology. Now, if you heard before about Motivic cohomology, you know that there are other definitions, like, for example, the Bloch's definition, or its different modifications by Suslin or Voevodsky. The difference is that those definitions, so they're very convenient definition, but they're kind of infinite dimensional definitions because they involve all cycles on your variety clause simplex, affine space. So it involves functions on the space of cycles, so functions on the space of functions. This involves only functions on the projective line, so it's kind of smallest possible definition which could possibly work, and so the question is whether this definition works or not. So as we have seen, it does work when the weight is 2, because in this case we have precisely this Bloch complex. B2 goes to wedge 2 of F star, and by theorem of Suslin it precisely tells you exactly what we want to know. And so the goal of the theorem which I wanted to prove in the end, so it is known, it was, I proved this about 30 years ago, that in this complex is also okay when you go to the next weight, but the case n equals 4, as you will see, is different for some reasons. And so the claim, which is the joint work with Daniil Rudenko, whatever I said today from the beginning about exponents of omega, this is a joint work with Daniil Rudenko, which is from University of Chicago, is to say that it also works, it also okay for n equals 4. And this implies Zagier's conjecture. Now what Zagier's conjecture says, I can make a statement. So it says, I mean, I can restate this as follows. When F is a number field, it's known that all cohomology which we see here are just here. So this is so-called Milner line, because here is Milner K groups. And this is, I would call, Borel line, because that's where K0 is concentrated when the field is a number field. And then the conjecture, this general conjecture in this particular case would say that this K2n minus 1 of F tensor Q is isomorphic to H1B of F4. And then the regulator map to R, whatever stands here, is the one which is given by the n logarithm here. And so this is the statement which, 4 logarithms, that's extremely important, yes. I'm not making any claims for n bigger than, Dima, yes, it's very important. But the conjecture is in general, the theorem is when n equals 4. So that's the statement. But now I want to connect back to the story I was talking about, symplectic form. So this is where you might want to somehow deloop your powers of your exponent of the symplectic form. But it turns out that this is not quite where this deloopment is going. And on the other hand, it turns out that if you want to understand why this conjecture is reasonable, you have to dig a little deeper. So you have to look at what's called Motivic Lie algebra. And so what we actually wanted to do, we want to produce a somewhat different complex, where this is a subcomplex. And then the claim is that we can deloop this powers of symplectic form on any class variety. as something as some cochain which lives in that complex. So I will explain on the next lecture what this complex is, number one. Secondly, why it's important to talk about this complex, because otherwise, as I said, it looks maybe nice, but it's not clear what's the meaning of this. So why Motivic complex looks this way and not that way. So this will make it a little bit more clear. And more than that, so the statement half of the proof that this statement is true for n equals 4, and it turns out to be also, you can do other case n equals 3 as well. So the proof goes through this delooping of the symplectic form. So delooping of symplectic form provides you all the kind of things which you need in order to prove the non-trivial part of this, half of this statement. And so this is how this kind of upgraded symplectic geometry works with application to Motivic cohomology or number theory. But I believe that's not that's not all which happens here. So I'll try to explain. It seems to me that what the story tells us, that there is some kind of quantum version of the story which is going on, which is the reason why, for example, we see symplectic geometry, which when we start talking about Motivic cohomology, which we haven't seen before. And in the small weight, we already know how actually the story is quantized. So probably it's quantized also in higher ends. And this is probably why this story is important for things like symplectic geometry of cluster arrays. Okay, that's it for today.